Hello world, welcome back to Codynamics. In this video, we are going to see how to mesh multiple bodies using cfMesh. So this tutorial will be mostly suitable only for external flows like what you see on the screen. So if that's your requirement, then you can follow this tutorial. This procedure might not be suitable for internal flows. So if you are interested in external flows with multiple bodies, then you can follow this tutorial. I will try to post a different tutorial for internal flows later, but for now it would be just external flows. Okay, now let's get started with the tutorial. So I have created a folder like this in any location, and I'm going to use OpenFOAM version 2506, which comes with cfMesh installed, so you don't have to install it externally. Now what I'm going to do is I'm going to open my command prompt in this location, and I'm going to open my VS Code in this location. Okay, so if you have VS Code, then you can use it like this. Otherwise, I would suggest you to install VS Code and then follow it. Okay, now since we have this, here we have to create certain folders and files. So what I'm going to do is I'm going to open the tutorial folders of cfMesh. So this I have installed externally. Actually, if you go to the cfMesh website, so which you can find from here. So if you just search for cfMesh open source, and if you download it for Windows, you will be able to install it, and after installation you will be getting a tutorials folder, something like this. So I'm just going inside here, and inside Cartesian mesh you can choose basically anything. I'm just choosing this bunny of tree, and what I'm going to do is I'm going to copy this system folder and I'm going to place it. If you go to your VS Code, you should be able to see that you have a control dict. It really doesn't matter what is inside your control dict, but one thing that you might have to change if you're using the same version, then instead of this uncompressed, change it to off. Otherwise, it will give some errors. Other things you don't have to worry, it's not directly related to the meshing. You can change these control dict files, FE scheme and FE solution while you are actually setting up the case. For just meshing, you don't have to worry about what is inside. Okay, now we also have this mesh dict, which for now you can just safely delete everything, and you don't also have to worry about this FE scheme, FE solution, or decompose part. So we are just fine with just these. Now what I want to do is like I'll open my WSL here, and then I'm going to create a paraview file. So I'll just call it touch space para.foam, and it will create a paraview file. Now let me open it. It will not have anything inside. So this error might pop up. You can just close it. It's not error, just warning. So there should be nothing inside for now. You don't have to worry. So what we are going to do is we are going to download this STL file. So actually I have already downloaded, and actually I have downloaded the step file instead of STL because that's usually better. What I'm going to do is I'm going to create a folder here called geometry, and then I'm going to place the step file inside this geometry folder. Okay, now I have copied my Airfoil step file inside this, and I'm calling it airfoil1.stp. Now I have my FreeCAD open, although you can use any CAD modeling software to do this procedure. Since we are focusing just on open source tools, I'm using FreeCAD. So I will just open this in my FreeCAD, and you will see an airfoil like this. This is the step file. So if you go to the mesh module of that, you can choose this option, create mesh from shape, and you can choose 10 micrometers with 5-degree deviation. Click on OK. It should immediately give you a STL file or the mesh file in FreeCAD terms of this step file. Okay, so this is what we have. Now you can hide this using a space bar. Now we have this STL file. Now if I click this button, it would export mesh. So you have to be careful. You have to save it as ASCII STL, and I'm going to call it airfoil1.stl, and then when I save, it will get saved. Okay, we have it here. Now I can visualize this in my paraview. You can drag and drop. Okay, now there is a problem with this file. So the problem is, since we converted it from step to STL, you see in the right side bottom, my step file has 2723 millimeters, but STL files do not have any dimensions or units, so it would be 2000 to 723 units, which is in meters in OpenFOAM terms. So it's basically 2000 meters long, which is 2 kilometers long, which we do not need. So we have to scale it down. So we are going to see how to scale it down. So I'm just going to open one of my terminals here, open WSL here, and we are going to use surface convert and then scale 0.001 because we are scaling down by a factor of 1000. And then you can type airfoil.stl, which is the input file name, and then we also have to give the output file name. So what I'm going to do is I'm going to type it as airfoil1s.stl. So S for scaled. You can have your own convention. So I'm just scaling it down. Okay, now you can see the bounds is slightly different. Open this. You can't even see it because it's very small. So even if you keep scrolling, you won't be able to see. So you can press something like this button and then it would just zoom to fit. Okay, now I can choose solid color and I'll get something like this. Okay, now if you see the data access grid, you can see it's within the control. It's less than a meter, which makes sense. Now this is just one airfoil. To make another one, we are going to make a copy of it. So we are going to use another OpenFOAM utility called the surface transform points. So if you just type surface transform points -help, you will be able to see there are a lot of features. So we are going to make use of this feature called the translate. So the way to use it is just type surface transform point -translate and then we have to give the coordinates. So I can just open the brackets, and if you see here, I open or choose data access grid, you can see it goes from minus -zero point 0.4 to around 0.1. So let's start with 0, 0. So x no deviation, y no deviation, and z we are going to move it by some distance. So maybe I can call it 0.2. Okay, so let's start with 0.2 in the z direction. I'm just moving it, and we have to give the input file name, which is going to be, okay, I have to close my quotations. Okay, airfoil1.stl, this is the input file name, and then I have to give the output file name, which would be airfoil2.stl. okay, I made a mistake. This would be airfoil1s.stl because this is the scaled version. I'm going to call the output file as the airfoil2.stl, or maybe just to maintain the convention, we can keep it as airfoil2s.stl. Now when I press enter, it should create another file, and let's try to open it here. Okay, it's too close than what I had expected. We can hide this. So instead of 0.2, I'm going to use 0.25. Just press up arrow and reuse the same command. Just 0.25. Okay, now if I go here, right click and reload files, reload existing form. Okay, now this makes sense and this is desirable. Okay, now we have airfoil1s and airfoil2s.stl, but now we also have to create a bounding box, right? So what I'm going to do is I'm just going to go to the system, and I'm going to go to the tutorials of OpenFOAM version 2506 and go to the simple foam motorbike and copy the block mesh dict from that and then paste it in this system. Okay, if you go to your VS Code, open this block mesh dict, you'd see something like this, and we don't need these many discretization. We can just keep 111. So I have explained why we should just use 111 in my previous cfMesh tutorials. So if you have not watched them, I highly recommend you to watch that first and then come back here, so it would make more sense. Okay, now we have 111, and whatever is there, we will just, okay, not this terminal, we have to go to this terminal where we have the airfoil case. Okay, so I'll run block mesh. Okay, it's trying to read the application here. Okay, let's put something. cfMesh. It really doesn't matter what you put here. So let's just put cfMesh. We run block mesh, and now we would have block mesh in that. So if you go here, click para.foam, refresh, you would be able to see a block mesh. If you go to wireframe, you can see like this, but we have it too big. So what I'm going to do is I'm going to turn on just data axis grid on one of these. And let's do one thing. Just for x-axis, let's first try to fix them. So in x-axis, you can see it ranges from minus 0.5 to 0.5. So in the block mesh depth, what I'm going to do is to change minus point. Okay, let's increase it by factor of 0.5. So I'll just put 1. Similarly, I can just change for other things as well. This minus 5, I will change it to minus 1. Save it, run the block mesh again. Come here, click para.foam, and then if you press refresh, now X is very close. So I'm just making it very small domain because my meshing process will be faster, but ideally this is not suitable. So we might have to keep whatever is recommended for external aerodynamics way. So you might have to keep 4 times the chord length or 8 times the chord length, depending on what type of analysis we are doing. Same for front and back, you would generally keep a longer distance in the front and even longer distance in the back. But just for tutorial purpose, I'm going to keep it slightly closer since the meshing process will be faster. Okay, so in the y-axis, if you see, the minimum is actually 0, so we can change it to minus 0.5 since we are increasing everything by 0.5. Minus 0.5, and maximum we can say is 1. So I'm just going to change this to 1.5. Okay, we'll save this, run my block mesh, and if I hit refresh, okay, now it came closer. It makes this a bit smaller, but it's okay. As I said, just for tutorial purpose. And in the z-axis, you can see it is probably around 0.1, so this would be 0.25. Let's try just 1.5. Okay, just try 2.5. If it is too big, we can make it smaller always. It is still big. It should have been 0.5, not 2.5. Okay, but the lower part is still intersecting with it. So let's do one thing. Instead of this 0.5, let's keep it as 1. And let's make these as minus 0.5. Run it. Okay, now it is okay and I like it. So you have to choose the dimensions based on how you need it. Okay, I will just hide the data access grid. Now we can work on the inlet outlet part. So if you see here, the front and back right now is basically the inlet and outlet. So we have to change it. So what I'm going to do is this inlet and the outlet is basically our front and back. So I'm just going to randomly copy or cut from front and back and place it here, hoping that the inlet and outlet would be the correct way. I'll save this, run it, and if you go here and refresh, okay, this is the front and back, which is correct, and the inlet is also correct. Then we have the outlet, which is also correct. Upper wall is correct, and lower wall is also correct. Okay, now we have proper inlet, outlet, upper wall, lower wall, everything. Now we have to make this as an STL. So how do I do it? Again, we will use an OpenFOAM utility, which is foam to surface, and then we have to give a name. So I'll just call it boundary.stl. Okay, actually, we have to give boundary.stl hyphen constant. Okay, so we got boundary.stl here. If I open it here, you can see now I have a boundary.stl with each patch under one color. Okay, now what I'm going to do is I'm going to copy or cut this boundary.stl, put it inside this geometry folder. Let's go to the geometry terminal, ensure that you are inside geometry, and we are going to concatenate three of the STLs. So which is cat airfoil1s.stl, airfoil2s.stl, and boundary.stl, and the output will be in geometry.stl. Just type this and you would get a file called geometry.stl. If you open this in your paraview, hide everything else and go to wireframe, you should be able to see all the geometry. So you have the boundary, airfoil 1 and airfoil 2 as well. So this geometry.stl is what we are going to use. So cfMesh usually takes in inputs in terms of fms. It works better in fms format than stl. So we have to give it in fms. Before seeing that, we will see what should be the feature angle for this. So if I just choose this airfoil1s.stl and go to filters, search, and choose feature edges, click on apply, and maybe hide this, go to solid color. Yeah, so you can see for 30 it is like this, but if I go to 60 it should technically remain almost the same, but if I go to 90 it should miss on some of the features. Yes, you can see. So as I increase the feature edge angle, it misses on some of the details of the geometry. If I go to 120 it should miss almost everything, and if I go to 180 it misses everything, right? So I think 30 should be good, but for even better thing, let's choose 15. Yeah, I think 15 is much better than 30 as well. So let's choose 15. And how do we use it? We chose it, but how do we use it? So we go here and type surface feature edges, and you have to give an input name. In our case it's geometry.stl, and then our output name, which is going to be geometry.fms, and then you have to pass in an angle, and I'm going to choose just 15. Actually 30 should work fine, but I'm just trialing here. I'm going to give 15. You can choose whatever angle suits for your geometry. Okay, I gave it as 15. Now we have geometry.fms. Copy this, put it alongside your system and constant folder. Okay, now we can go to our VS Code, choose your mesh deck. Now what I'm going to do is I'm going to go here where we have all the tutorials of cfMesh. So you should be able to see these four folders, and I'm going to search for mesh deck. You should be able to see a bunch of items here, around 14 files. Choose all, just drag and drop it on the right side. So if you just move your mouse to the right, you will be able to put it on the right side of your VS Code. And now what you are going to do is you are going to just copy the header. It's not mandatory, but okay, just to keep the convention, we will have it. And the first thing that we have to do is choose the surface file. And in our case, the surface file name is geometry.fms, and then don't forget the semicolon. I can change this type to C++, and the footer is also going to be placed. Just in case, it's not mandatory, but you can keep it. And then we also have to define the maximum cell size. And initially, I'm just going to keep it as 0.2. We are going to trial it out. Okay, so we'll start with a bigger size, which is 0.2. And here, okay, on the airfoils, so if you just type, you should be able to see the geometry.fms. Here you can type Cartesian mesh. So if you type that, press enter, it should take a bit of time and it would give us some mesh. Okay, the meshing is over. What I'm going to do is I'm going to go to this para.foam and just going to choose it. Click on refresh. Yep. Now we are able to see that we have gotten a mesh here. But this is certainly not the type of mesh that we would prefer. So there are a few problems that occurred here. Let's address it one by one. So if you go to this geometry and choose the geometry.htl, if you just keep scrolling down, you'll be able to see that this is called a Epler 1230 meshed, and just search for solid. Yeah. So again, see, it's called as Epler 1230, Epler 1230. So this name is actually coming from our original STL. So this airfoil1.stl, all this has that name. So we have to change this in order to use proper local refinement. Otherwise, we would get patches like this. Okay, so we are going to change it now. I'm doing all this and then going and changing it because in one of my videos I explained this, and I was getting comments on why we are doing this, what was the purpose. So that's why I demonstrated it first. So what I'm going to do is I'm just going to open this Airfoil 1s and Airfoil 2s in VS Code, and if you just see the first line, you will be able to see solid followed by some name. So I'm just going to change that name to airfoil2.stl because this is airfoil2s.stl. And if you go to the last line, you will be able to see something like this. So here also I'm going to change it to airfoil2. Okay, by the way, you don't need this .stl, you can remove it. Just airfoil2 is enough. Similarly here, and then make sure that you have one empty line at the last. Similarly for airfoil 1, you can change it to airfoil 1 and go to the last line. Again, change it to airfoil 1, save it, and then again we can go to our geometry. Here we can concatenate them and then convert it to FMS. Okay. Now if I take that FMS, put it here, replace it, and then run this Cartesian mesh, you will be able to notice a few things. The first thing, it would run slightly faster. The other thing is that we will get proper namings out of the mesh. So here now you can see that we have this meshed, all that. So this will go away after we change the name. Again, we would have airfoil 1, airfoil 2 and everything, but the naming will be much better to understand because we coded it. So I'm going to delete it and then open the para.foam again. Now you can see we have airfoil 1 and airfoil 2 properly defined. So if we go to wireframe, again the mesh is bad, but you get the idea. We have airfoil 1 and airfoil 2. So we can easily visualize by just choosing that. Now we are going to do certain things. The first thing is go to the mesh depth, and instead of 0.2, let's choose somewhere like 0.1 or even 0.08. Okay, and let's run the mesh again. So we are choosing a smaller cell size. So now the mesh should be slightly better. Okay, the mesh also ran faster. Hit refresh. Yep, it looks even better. And if you choose internal mesh as well, yeah, the overall size looks comfortable. I mean, like it is medium size, not too coarse. So we can't keep reducing the overall size because eventually the size is going to blow up, and the background mesh need not be this fine, if you know. So we will just refine the airfoil using the local refinement, and we will keep the overall size slightly bigger. So the way we are going to do is we are going to choose the maximum cell size as 0.1, and then we are going to create this local refinement, and then we are going to first call airfoil 1. This is the name that we are getting from the STL. So airfoil 1 we will put as cell size 0.05 probably, and we will also do the same for airfoil. Okay, and then let's run it again. It definitely ran faster now. Okay, now it looks even better, but the mesh is still not very good. So we can actually make the cell size smaller for airfoils. So let's put it as 0.2 and run it again. Okay, is it better? Yes, it's definitely better. Now what I'm going to do is I'm going to create another paradox form here, and then I'm going to choose a slice, show plane. Okay, we can hide this for now. Go to surface with edges. You can see triangles. To hide it, you can choose this triangulate the slice. Still, you might see these lines. So there is a small trick. Show plane, and then slightly move this green plane front or back. Click on apply. Now those annoying lines will go away. We can snap it to x-axis. You can see it looks slightly better, and the tail is also properly captured, kind of properly. I wouldn't say very proper, but kind of properly captured. Now we are going to see how to add layers. Till this point, we know how to add multiple geometries. This would work even for 3 or 4 geometries, and we know how to name them properly. So we have the inlet, lower wall, outlet, upper wall, front and back, everything properly defined. And we also now know how to add local refinement. We also know how to change it. Now we will see how to change or how to add the boundary layers. So if you just keep looking for other tutorials, yeah, I think this one might just suit, but we'll go for a simpler one. Yeah, so we have this boundary layers function. I just added. The order doesn't matter. You can choose this boundary layers, and this is actually the default value. So if you don't define it for any of the patches, then what should be the thing? But we don't have to do that. So I'm just going to choose this patch boundary layers. I'm just going to choose Airfoil 1. Okay, and I'm also going to do the same for Airfoil 2, except I'm going to keep the first layer thickness differently. Okay, so if you keep searching, yeah, we have something called the maximum first layer thickness. So here I'm just going to keep it as minus 0 point, probably 0.005. Ideally you should calculate the y plus input, but since this is tutorial, I'm just teaching you how to use the software. I can save this file. Okay, I was telling I would use a different one, so let's choose 0.001 here. I'm going to run the Cartesian mesh again. Okay, I am going to refresh it. Okay, there are layers, and let's see if there is any difference between those two. I don't see much difference. Okay, then I can safely say it has hit a bottleneck. It's not going further down on some sizes. Let's look at the tail. Okay, it's still better. Okay, let's do one thing. We'll go back, choose 0.001 to this, and then let's choose 1e minus 6 for this and just see what happens. Okay, now if I hit refresh, you can see the airfoil one has only gotten worse. It did not get any better. So it was better at 1e minus 3 and not 1e minus 6. So let's just save this, and you can run the Cartesian mesh again just to get a good mesh. Okay, now the mesh is better. Now there are certain things that we can do to this boundary layers. One is optimization. So if you check the previous tutorials, yeah, we have something called the optimize layers. Similarly, yeah, this is what I was looking for. You have this, so you can see the number of smooth normals and the recalculate normals, the relative thickness tolerance. There are some of the optimization parameters for meshing here. So I'm going to choose whatever is given in the tutorial. I'm going to run it back. Okay, I have placed it inside patch boundary layer, so I cannot use it. I have to place it outside this. It should be adjacent or along with the patch boundary layers and not inside it. Now we can run it back, refresh. I'm not sure how much it has optimized, but it really does look better to me. So you can let me know your comments in the comment section. Okay, so this is how we do the meshing for multiple bodies in cfMesh. Now let's do check mesh. Okay, there are less number of faces that are skewed and some non-orthogonal faces, but looking at the overall number of cells, that does seem pretty low. So if you are okay with it, it's fine. Otherwise, you can also improve it even further, and it's up to you. So I hope this video was useful. If you want anything specific in cfMesh or OpenFOAM or other CFD related open source tools, please drop it down in the comment section. And if you like this video so far, consider dropping a like, consider subscribing to the channel. And if you think this video was useful, you can share it to your peers. It would greatly help us. So see you in the next video. Until then, happy learning.